Hello! In this section, we're going to talk about how to optimize the performance of our Node applications. Let's start with a quick recap of our Node fundamentals. Our Node servers normally take in requests and process them on the event loop, sending back the response to the browser. This all happens on one thread. Your Node server, all of the JavaScript code you're running, and the event loop are on a single thread, which means that they can only ever run one line of code at a time, processing one request at any point in time. That event loop is generally pretty good at juggling multiple requests as they come in and passing off any hard work so your server doesn't freeze, or as we call it, it doesn't block. Let's go back to our more detailed view into Node's internals from earlier in the course. Node and the event loop can juggle these multiple requests coming in by taking advantage of the many threads that your operating system already has, and by taking advantage of the thread pool. Node makes use of them by passing off input and output tasks that take a long time to complete. It tries to pass off these long-running tasks to your thread pool and to the operating system so that your JavaScript code and the event loop don't block. For example, if you have a Node server that handles an incoming request by reading and writing to a file on your machine or on another server, in that case, Node passes off the work to read that file to the thread pool, and your JavaScript code doesn't block, even though that JavaScript code is itself running on a single thread. As we've seen so far, in the vast majority of Node applications, this setup works great. Node is ideal when working with non-blocking operations, for example, making requests to servers hosted somewhere on the internet that do things for us and that we can put together into a meaningful application. However, sometimes we have some code that requires a lot of processing power, code that blocks our event loop from continuing, code that doesn't involve our basic file and network operations that Node knows how to handle efficiently. What happens when we need to do a lot of the heavy lifting in JavaScript? JavaScript that only runs on a single thread. Let's investigate this and use what we learn to really optimize the performance of our Node web servers, especially on machines with multiple cores. All of this can get a little bit confusing to talk about in theory, so we're going to start by building out a simple example which will demonstrate some of the challenges that we might encounter. We will then use this example to try a few approaches to improve our server's performance. Let's dive in. Welcome back. Before we demonstrate how we can improve performance, we first need to show how we might run into performance problems. Let's start by building out a very simple example to show the effects of blocking the event loop in a Node server. I'm in my performance example folder here, which is going to be an Express server. So in our terminal, let's create a package for our server with our npm init-y command. And now that we have our package.json, we'll npm install Express. Now our server code is going to live in server.js, which is going to create an express application. So const express equals require express. We'll initialize our express application, const app equals express, and we're going to have two routes. One, an app.get route at our main root endpoint here, which takes in the request and the response, and is just going to respond with, so using our res.send function, we're just going to say performance example. That's the name of our server. And our second route is also going to be a get. This time, we're going to call it the timer. And we'll see why in just a second. So it also takes in a request and response. Now, it's going to delay the response for a few seconds before responding back to the client. So we'll delay the response, and then we're going to send. After our timer has completed, we'll try to wake the user up by saying, ding, ding, ding. How are we going to delay the response? For the sake of our example, we're going to take this naive approach by writing a function that we'll call delay, and it accepts an argument called duration, which is the amount of milliseconds the function is going to wait. Now, here's the catch. The way we're going to delay is by basically spinning in place, doing nothing in JavaScript, with a while loop, which checks basically the start time of when we call our function. So start time will equal to date.now, which is the current time represented in milliseconds. And our while condition is going to check date.now as well, minus the start time when the function was called, checking that the difference in those two times has been less than the duration of our delay. And inside of our while loop, well, we're not going to do anything special. We're just going to constantly check whether the current time minus the start time has been less than the duration of our delay. Our JavaScript will loop over this condition until we've been waiting longer than the duration. And while JavaScript is checking this condition and looping over it, well, our event loop will be blocked. JavaScript code, like our delay function, is processed on the event loop. It's not a file or network operation, so it's not going to be sent to the thread pool or passed off to the operating system, like many of our built-in node functions. Instead, while we're in our loop, the event loop is completely blocked. This means that if we call our delay function in our timer endpoint, passing in some amount of time, let's say 9,000 milliseconds or 9 seconds, our server can't do anything else while our delay function is executing. It can't process other requests or parse any files or make queries to our database. No other JavaScript code will be processed. Let's find out what effect this has on our server. So we still need to call app.listen, and we'll listen on port 3000. Any port works here as long as it's not conflicting with another server that's running on our computer. And now I'm going to run npm start. When that's started, let's go to our browser and try to make some requests against our server. Let's open up our JavaScript console here, going to our network tab, and try to make some requests to our server at localhost on port 3000. Let's go to our root endpoint. Looks like that's working. The request took about 189 milliseconds. I have a lot of different applications running on my machine right now. Normally, this request would take less than 20 milliseconds. One of the challenges in this section, and with measuring performance in the real world, is that the exact behavior depends on the conditions of your measurement. The applications you're running, your CPU speed, your operating system, even your version of Node can all play a role. Because of that, I encourage you to follow along with this section and play around with how the server responds on your machine. It's likely you will see at least some differences compared to what I have here. What I can guarantee is that the same concepts we're learning apply regardless of your machine. But let's see here. The first request often takes a little bit longer. If I make it again by refreshing, we're getting about 145 milliseconds. Now in the timer route, we can go to /timer and wait around until our server responds after just over 9 seconds. Our delay function is simulating some work that takes 9 seconds to complete, just like we expect. Now, here's the catch. If I go to another tab, and I open up my network tab as well, network, and let's say I go to the /timer endpoint here, and then really quickly switch to the other tab, and try to load the same endpoint. How long will it take for my response to come back from the server? Let's see. In the first tab, we'll go to the timer endpoint and quickly refresh the other tab. We can see the response is pending in the second tab. It's come back after 9 seconds in the first tab, but in the second tab, it's still pending. It's only after 19 seconds that our response came back. That's more than twice as long as it should have taken. This is crazy. Because the first request blocked the event loop, the second request wasn't able to start. The Express server wasn't able to respond to it until the first response completed and that timer expired. Our CPU and the event loop are really busy here, spinning on this condition as fast as our CPU can go. Our event loop won't continue until our delay function returns, which means our server won't be able to respond to any requests. If we go back to the browser, and in one tab I go to the timer endpoint, and in the second I go to the root, even though the root should only take about 100 milliseconds to complete, it actually ended up taking 6.5 seconds, because even after I switched tabs and pressed refresh, which took me about 2.5 seconds, the timer endpoint was still executing. Our blocking code is slowing down the entire server. There needs to be a better way of handling this so that our server doesn't grind to a complete halt. Let's keep going and investigate some different approaches we can take to improve this situation. But first, I know this example is a little bit contrived. It's not every day that we write while loops that don't do anything for a certain amount of time. So let's explore some real-life examples that behave similarly. I'll see you in the next video. Welcome back. In the previous video, we saw that blocking functions, like our delay, could cause our entire server to massively slow down. Our delay function isn't very realistic. We could replace it with a non-blocking call to set timeout, for example. What are some examples of real-life functions that act like our delay function, blocking the event loop? Two functions that you're very likely to see are the json.stringify and json.parse functions, where json.stringify takes in a JavaScript object and returns the string representation of that, and json.parse does the opposite, where it takes a stringified object and returns the corresponding object, while stringify returns the string representation. And let me comment these out. Now, with typical objects, these functions don't quite take 9 whole seconds to complete. They'll finish in just a few milliseconds, even for large JavaScript objects. However, if you have a server that takes in many requests, this can add up, especially if every single request is making a call to json.stringify, which is common, for example, when logging objects. If calling this function blocks your server for 10 milliseconds, and the rest of your request takes 10 milliseconds, you've now doubled the time your server is responding to that request. But more importantly, that's 10 milliseconds that your server can't respond to any other requests. A second request that comes in won't even be able to start before your blocking json.stringify call returns. This can quickly spiral out of control. Now, some other common functions to watch out for are sorting arrays. For example, using the array.sort function. Say we have an array of 5 numbers. If we call .sort, we're now blocking the event loop while these numbers are sorted. For very large arrays, or for very large objects, these functions can start to get very slow. We also have certain functions in Node's built-in crypto module, which has functions related to cryptography and security, which are designed to execute slowly, so that it takes longer for hackers to guess your password. For example, we have the crypto.pbkdf2 function, as well as the crypto.scrypt function. These are both what's known as key derivation functions, which we use to create hashes of users' passwords, so that our servers don't need to actually store the user's passwords in plain text, but instead as this hash, which usually looks like a series of random letters and numbers. We want it to be expensive and time-consuming to use these hash functions so that hackers can't check tens of thousands or even millions of passwords per second, but instead they need to dedicate a significant chunk of their computing power, even for one password. When it comes to security, we have this funny reversal where slow blocking functions are sometimes what's actually desired and are better than having quick, easy-to-compute functions. What we're doing with the delay function is simulating the extreme worst case of this blocking behavior by having a function that completely blocks the event loop for many seconds. 9 seconds is like 9 years when it comes to response time. Typically, for real-life applications, you want to keep your response times below 100 or 200 milliseconds at most. There have been studies that show how response times are perceived by humans when it comes to the web and applications. And it's been shown, going back to even 1968, that about 100 milliseconds is the limit for you and I to perceive something as reacting instantaneously. That's what we want. And any longer than 1 second, and it's likely that the user's flow of thought might be interrupted. You may start losing context on what you were trying to do. Any increases beyond about a second are likely to show a progressive decline in the amount of users who stay engaged with your website. If I scroll down on this article, we have an example where load times longer than 3 seconds resulted in 73% of users losing interest. Now, of course, it depends on what your site is doing. So if the user expects a large file or video to be loaded, they might be a little bit more patient than if they are expecting real-time stock and investment information. But for sure, if I click submit and nothing happens for 9 seconds, I'd leave the site for sure. Spinners and loading indicators can help, but after a point, they can become annoying. If you're running an online store, for example, you can use this information about how many users leave your site based on response time to calculate how much revenue each added millisecond loses your store. You can take the average amount of money that your users spend on your site in your store and multiply that by the amount of users that become disinterested when the loading time is past a certain point. These are just a few examples. Needless to say, there are strong arguments for having performant servers and low response times. Now that we know what functions to look out for, and we know why having low response times is important even if our event loop is blocked, let's find out what we can do to improve the situation. We have some good options, so I'll see you in the next one. Welcome back. Let's look at the main approach we can take to improve the performance of our node servers. In general, when solving difficult problems, the best way to approach them is to divide your large, difficult problem into smaller pieces and solve those smaller, more achievable pieces. Similarly, when dealing with servers that are overloaded with too much work, we want to divide that work up and spread the load. How? Well, we know that the node.js process runs on a single thread. Node and JavaScript don't follow the multi-threading approach that other languages like Java and C++ follow. What we do in Node is run multiple node processes side by side, allowing them to share the work amongst themselves, like a team working together towards a common objective. With servers, the work that we take in is broken down into these requests that come into our server. And so, Rather than taking in each request and handling it in one Node.js server with one node process, we can instead spread our requests out between multiple Node.js processes that each respond to that request in the same way. They each contain a copy of your server code that's running side by side in parallel. And so now the second request can be handled by the second node process, and the third request can be handled by the third node process. And if we have more requests than servers, well, each of these processes can still handle multiple requests at a time. The important part is that they're now sharing the load equally between them. Using this technique allows your single-threaded node applications to make full use of all the CPUs on your machine. Remember, most computers today have multiple CPU cores that can each run code side by side without affecting the performance of code running on any of the other CPU cores. In the next video, let's take a look at one approach we can take to have multiple node processes working side by side to respond to multiple incoming server requests. I'll see you then. Welcome back. Our first approach to improving node performance is using the built-in node cluster module. The cluster module allows you to create copies of your node process that each run your server code side by side in parallel. The way this works is when you type node server.js to start your node application, the main node process is created. Node calls this the master process. Inside of the cluster module, we have access to this function called fork. Anytime we run the fork function in our server.js file, Node takes this master process and creates a copy of it that it calls the worker process. We can call this fork function however many times we like to create many worker processes that are attached to a single master. It's these worker processes which do all of the hard work of taking in HTTP requests, processing them, and responding to them. Each worker contains all of the code required to respond to any request in our server, while the master is only responsible for coordinating the creation of these worker processes using the fork function. In this example, where the fork function has been called twice, we now have 3 node processes running. The master, which we created ourselves when we told Node to execute server.js, and then the 2 worker processes that were each created by the fork function. It will be these worker processes that accept incoming requests and share them using what's called the round-robin approach, where it sends the first request to the first worker, the next request to the second worker, and because we only have 2 processes, the third request goes back into the first worker. The workers take turns responding to requests as they come in. And while not all requests are equal, some might take 15 seconds to complete, while others might be just a few milliseconds. In the grand scheme of things, this approach is simplest to implement, and you might be surprised that this round-robin approach ends up being one of the most fair ways of distributing work between the two workers. Even compared to fancy approaches that try to predict priorities and assign different importance or weight to each request. Round robin is a good approach. One little caveat is that on Windows, because of how Windows manages processes, Node makes no guarantees about using the round robin approach. Instead, to maximize performance, it leaves how to divide the tasks up between worker processes up to the Windows operating system. It could use round robin, or it could use a slightly different approach. Alright, that's enough talking about it. Let's see the cluster module in action in the next video. I'll see you really soon. Welcome back. We've talked about the theory, but how do we use the cluster module? How can we apply clustering to our node servers to improve performance? Let's go back to our performance example code and create two forks of our server which can each handle requests concurrently, side by side. First things first, to use the cluster module, we need to require our built-in cluster module, assigning it to a constant that we'll call cluster. Now we make our cluster of processes. Remember our diagram. When we type node server.js, what we call the master process is started. And it's from this master process that we can call our fork function to create these two worker processes. The worker processes that we fork run the same code that we have in server.js. The only way we differentiate our master process from the worker processes is by using the isMaster Boolean flag from the cluster module. So down here, right above our app.listen call, we can write if cluster.isMaster, and any code inside of this block will only get executed the first time that our server.js file is executed as the master. Let's log that to our console so that we can see the master has been started. And anything that we write in the else condition here is when isMaster is false and our code is running as a worker process. So we'll say console.log worker process started. What we're going to do is fork two workers which will run the Express server with the two routes that we've defined here. So from the top, we run node server.js, we're the master, and now we want to call cluster.fork. Each time we call this function from the cluster module, we create a worker. We can do this however many times we'd like, but let's just start with 2 for now, just like that. Perfect. What about the workers? It's only as a worker that we want to listen for incoming HTTP requests and handle them using our Express routes. So we'll only call app.listen when we're running as a worker process. When we start an HTTP server in one of our worker processes, whether it's Node's built-in bare-bones HTTP server, or whether it's something like Express, Node's cluster module understands the listen function. Node knows that each of our workers will be listening on the same port, on port 3000. And the Node HTTP server knows to divide incoming requests that are coming in on port 3000 between the different worker processes. For each request, in our request handlers here, let's use our template string to send not just the performance example text, but also we can use the built-in process module, the process module with our argv array, which we used to get the command line arguments to our Node programs. The built-in process module also has this process.pid property to get the ID of the current process from the operating system. This is useful to us because our master thread, as well as all of our worker threads, will have different PIDs to help us see that different processes are indeed actually handling different requests, that our processes are sharing the load. So we'll say process or performance example is running on this process, and our timer was run on process.pid. Now we'll know if our different requests are being handled on the same process or a different one. Let's run our tiny little cluster of 2 workers. We can start our master process by running node server.js or by typing npm start. They're equivalent. Beautiful! Our master has been started and 2 workers were created immediately afterwards to listen for incoming requests. Before we play around with our server to see how much it helps our clustering, helps our server to respond quickly, I want to reinforce just one important concept, which is that every time we call fork, when we're in the worker process and when we're in the master process, we're always running server.js. The code for each process is the same. The only difference is this isMaster flag. To demonstrate this, we can console.log right before our conditional to say running server.js. Now, what do we expect to see if we run npm start? Let's take a look. I'll Control-C out of our process here. This will terminate the worker processes as well. I'll also clear the terminal and run npm start. You can see that for the initial master process, as well as the 2 workers, our server.js code was executed. The first time, as the master, forking our 2 worker processes, and then the second time, as the worker, listening for incoming connections. Let's open up Chrome and test our cluster. In one tab, we're going to try to navigate to the timer endpoint. And in the other tab, the root, which should respond much quicker. Remember, when we had just one node process, the blocking timer request prevented our quicker root route from responding until it was finished. And trying to navigate to the timer endpoint in 2 different tabs resulted in one of those requests taking more than twice as long. So I'll open up the Chrome Network tab in our JavaScript console, first in one tab, and then in the other tab as well. Now watch out. Here's where we have to be careful. Chrome, and some other browsers as well, try to be clever. And if they notice you making two identical requests, for example, to the timer endpoint in two tabs in your browser, when Chrome detects that you make the same request at nearly the same time, it waits for the first request to complete before it even tries to make the second request, so that it can potentially reuse the response if the response is saved to your browser's cache. This is a little-known feature that can cause confusion if you're not aware of it. Chrome is trying to minimize the amount of traffic on your network. But this isn't great when testing our server's performance. So when testing our server clustering, what we need to do is disable the cache so that Chrome actually makes our requests side by side at the same time. So I'll make sure to select Disable Cache in both tabs. Or we could press the key combination to refresh without the cache. For example, Control-Shift and R, or Command-Shift and R in Chrome if you happen to be on a Mac. We're finally ready. Let's make our two requests in one tab to our timer endpoint, and really quickly I'll switch to the second tab and refresh there as well. First and second, we can see in the first tab, the connection is pending. I'm going to wait 9 seconds, and here we go. 200 response. And at the exact same time, I got back the response in the other tab. Both requests took 9 seconds. They were run in parallel on my computer because I have 2 CPU cores, and they were handled in 2 separate processes. We can see that we logged the process ID. For this request, it was 24730, and on this one, we have a different process ID. I could make a request to the timer endpoint in one tab, and in the other, go to the root, and the root request came back almost instantly, after 20 milliseconds. I now have a few less applications running on my machine, so the requests are coming back a little bit faster. But the difference is drastic. Our root endpoint here didn't have to wait for the timer in the first tab to complete. This is exactly what we want. We've solved our performance issues. Or have we? In the next video, let's discuss how to best use clustering in the real world. I'll see you soon. Welcome back. In the last video, we saw the huge improvement to our server's response time that clustering can give us. But our cluster has its limits. Let's set up another little experiment. Continuing from our example in the previous video, if I open up 2 more tabs, and I open the network console in each of the tabs, making sure that Disable Cache has been checked off, let's see what happens if I go to the /timer endpoint in all of the tabs at more or less the same time. So I start it in the first, in the second, and refresh my 2 other tabs. I'm waiting around, and the request came back after 9 seconds in the first tab, 9 seconds in the second. In this tab, I went to the root endpoint instead of the timer by mistake, but we can see even the root took 6.5 seconds, and our last request to the timer took nearly 16 seconds, nearly double as long as it should have. Only 2 of our requests were made side by side in parallel. The other 2 had to wait because those processes were already blocked responding to the first request to timer. Notice the process IDs that we logged. In the first tab, we have a process with this ID ending in 29. Then we have 30 for the second request. And using our round-robin approach to dividing work, we can see that the third request reused the first process, and the fourth request reused the second process. Using clustering is not what we call a silver bullet, something that solves all our problems just by always taking the same approach. We're limited by the amount of processes that can execute in parallel. Right now, in our cluster, we've forked 2 processes, and we could only handle 2 requests simultaneously at the same time. That means we should keep adding these fork statements to create more worker processes, right? Well, there's a limit to how far this approach can take us. Let me show you what I mean. Let's be a little bit more clever and automate the creation of our forks. We're going to use the OS module, which is another node built-in. So we'll say const OS equals require OS, which stands for operating system. And we're going to use the operating system to give us some information that will let us create the correct number of worker processes. You see, to run efficiently, each process needs to use a separate processor in your computer, in your CPU. In general, we want to limit the amount of forks that we create to the amount of logical or physical cores in your CPU. Physical cores are just that. They're separate processors in your computer that each handle work in parallel. Logical cores are a little bit more complicated. They use some fancy logic to let you run multiple threads in parallel on one physical core, but only in certain cases, and not as efficiently as a physical core could run your code. To maximize the performance of our server, in general, we want to take the amount of logical cores, which we can do by saying const number of workers equals, using our built-in operating system module, os.cpus, which gives us the amount of logical cores dot length. And we'll say for each of these workers, so let I equals 0, I is less than number of workers, and I++, we'll create our new fork. And I'll remove these extra statements. Now we're only creating the amount of worker processes which will maximize the usage of all of the cores in our server machine. That's what we want in the real world. So on my machine, I'll restart the server, and I have 4 physical cores, but 8 logical cores, which means I now have 8 workers. That means in my browser, I can make up to 8 requests at the same time and get increased performance. The 4 physical cores should allow our response to return for our timer in about 9 seconds, and the non-physical cores, so the 4 left over, might see some performance somewhere in between. Let's see. I'll make 6 requests in total. Again, opening the network tab, just to make sure that we're disabling the cache. And let's go. This time I'll make sure to hit the timer endpoint in all of the tabs over here. So first this tab, 2, 3, 4, 5, and 6. Let's wait around for the request to complete. All right, so we got the first request completing in 9 seconds, 9.06, 9.03, again about 9 seconds, and let's see how efficient the logical cores are on my machine. Looks like they're very efficient. It's possible my machine has 8 physical cores. That's a pleasant surprise. And the last request also took about 9 seconds. We're now maximizing the performance of our server based on the amount of CPU cores in our machine. Very good stuff. Welcome back. Remember how we mentioned the round-robin approach? Round-robin is just one strategy that is used for what's called load balancing. Load balancing is a fairly advanced topic, and you could make entire courses about it. But it's such an important topic when it comes to building backends that you'll gain a lot just from being introduced to this concept early. Load balancing is basically a way of distributing or dividing a set of tasks to a set of resources. For example, dividing which requests will be handled by which processes, if you have a cluster of worker processes for your server. When we talk about load balancing, we use what's called a load balancer to determine how, for example, our requests should be divided among the different processes handling them. The load balancer is what takes requests from users and distributes them so that the responsibility of handling those requests is shared by many different processes, or potentially many different applications or servers. For example, you could have 2 servers, 2 different machines, each running a set of processes that can handle requests. So you're balancing the load of requests both to 2 possible different servers and to many different processes inside of those servers. Load balancing applies when you're running multiple servers or processes in parallel, each handling the same kind of request, just like we saw in our example, using the same set of possible routes. You might hear load balancing talked about in the context of what's called horizontal scaling, where horizontal scaling is a fancy term for what we've been doing in our cluster. Rather than doing what's called vertical scaling, where we add more speed to our one node process, our one node server, by, for example, replacing our CPU with a faster one. That's vertical scaling. For horizontal scaling, we instead take our server, and it doesn't have to be super fast or big, but we grow or scale our application to handle more requests more quickly by adding more servers, or in the case of our cluster, more node processes. That's horizontal scaling and load balancing in a nutshell. the two most common strategies for distributing requests that are used by load balancers in the case that we have no prior knowledge about how long a request will take to complete, which is usually the case when we have servers with many different types of requests that can sometimes take longer and sometimes take much shorter. Well, when we don't have that rigid predictability, the two main approaches for load balancing are round robin, which we now have quite some experience with, and basically just randomized distribution of requests. Each new request is assigned to one of the processes at random. Believe it or not, these ridiculously simple algorithms for deciding which process should handle a request are actually the most effective when you don't have really good knowledge about exactly how long a request will take to complete. To summarize, in Node, we can use the cluster module to do load balancing of requests as they come in to our Node HTTP servers. And the cluster module uses the round-robin approach to determine which process will handle those incoming requests. The requests, which are the load being balanced across your server. Just a little bit of theory to reinforce what we've been talking about. All right, I'll see you in the next one. The cluster module is a great tool to improve the performance of our servers. However, there are many other features that are commonly asked for when running clustered servers in production. The good news is we have a really superb tool built on the functionality in the cluster module that includes any functionality you could possibly need. This is the PM2 tool. PM2 uses the cluster module internally, which we can see if we go to the documentation under cluster mode. Under the hood, it's using the cluster module that we're already familiar with. So what we've learned applies. But PM2 provides many added capabilities to help you manage that cluster. You may want to restart your cluster processes if there's a code change, just like we do with NodeMon when running just one process. For that, we can see PM2 has a watch and restart mode. Or you may want to restart processes automatically if there's a failure in one of your processes. So we can look at restart strategies or graceful shutdowns. We might want to monitor the status of our processes or manage where the logs for each process go. PM2 is really rich when it comes to features, and it's widely used even in projects that don't use Node. We can find PM2 in our npm registry and use it as a tool just like NodeMon. In the next video, let's set up PM2 and explore how to use it to manage a cluster of Node processes. I'll see you soon. Let's get PM2 installed on our machines and see how it can help us to manage a cluster of worker processes. By the way, PM2 stands for Process Manager 2. Why 2? What happened to Process Manager 1? That's a mystery shrouded in secrecy that we'll probably never find out. All right, PM2 is on npm, so to install it, in our terminal, we can do npm install PM2. Now, I suggest you include PM2 in your dependencies by saving it to your package.json, just like we do with all of our other dependencies. So I'm going to install PM2 as a local package in our performance example folder. It's not a development dependency because we'll be running our node server with PM2 in production. However, for convenience, many people like to install PM2 as a global module, which you can do by using the -g flag when typing npm install PM2-g. I'll do that here as well to make it easier to demonstrate some of the features inside of our command line. PM2 is now installed as a global module, so I'll clear the terminal. We can now run PM2 directly and use it to manage our server process. We have the PM2 command. Let me make this a little bit smaller so you can see. And the PM2 tool takes in different commands, which we can use, for example, to start our server process. The most basic way of using PM2 is by passing in the start command, followed by the JavaScript file we want to run. In our case, server.js. PM2 has now started our server, and again, let me make this a little bit bigger. We can see that we have one instance of our server, and it's currently online using 0% of our CPU and about 8 megabytes of memory. Just like before, we can make requests in our browser to our server at port 3000 and, for example, hit our timer endpoint and the root in a second tab. This part hasn't changed. Back in our terminal, notice that PM2 is running in the background. I can type other commands into the terminal, and the server is still running. We can list the processes that are being managed by PM2 with the PM2 list command. You can also use PM2ls or PM2 status. If we type one of these commands, we get the current status of our server. We have one process. This is our master process that's being managed by PM2. We'll see how to manage the worker processes in just a second. But we can stop our server by typing PM2 stop and typing in the ID of the process or the name, so server. We can start it back up again with PM2 start server, this time calling it by name. And if we wanted to terminate it and remove it from the list of processes managed by PM2, we would type PM2 delete server. All right, this is all fine and all, but why do we really want to use PM2? Well, PM2 comes with clustering built in, which means that we can simplify our code to remove any usage of the cluster module. We don't need to fork inside of JavaScript because instead, PM2 will fork our process. Our code in server.js here will be run as the worker process, so we don't need to check the isMaster flag, for example. We can get rid of our entire master block here and leave just the worker process aspect, where we listen on port 3000. Let's remove our comments here as well, and we can get rid of our cluster module from the imports, as well as the OS module. Much simpler, right? To start a cluster in PM2, what we'll do is run our PM2 start command for server.js, this time passing in the -i flag. I for instance. It measures the amount of worker processes that will be created in our cluster. We can type a number like 2 to start 2 workers, or max if we want to start the maximum amount of workers to take full advantage of the amount of CPUs in our machine. You can see that on my machine, 8 processes have been started and are being managed in our PM2 cluster. Just like when we were using our cluster module, we can make 2 requests side by side, say to the timer endpoint, and they're executed in different processes. One request doesn't block the other. In fact, remember, the PM2 tool takes advantage of our cluster module under the hood. We can always write PM2 list to show the current status of our server. And you might be asking, if PM2 is managing all of these processes, where do my logs go? Why am I not seeing any logs in the terminal? We can always type PM2 logs, and we get a real-time view of what's being logged in our server right now. In fact, as you can see, the output is saved even when we stop our server. So I can Control-C out of this and restart our cluster by writing PM2 restart server. Our list now shows that each server has been restarted once. Each process is using a little bit of our CPU because it's just starting up. And in our logs, if I type PM2 logs again, this time I'll exit out of this and type PM2 logs -- lines 200 for the last 200 saved lines of logs. And we can now see that our historical logs are preserved. For example, we see that we restarted the master here at some point, even though our current code doesn't include any logs for the master. This log is from when we ran PM2 start while still using the cluster module in our server.js. PM2 includes a lot of advanced logging functionality, including sending logs to a file, and even doing log rotation, so that the server doesn't get overwhelmed by one giant log file like we discussed earlier in the course. We'll demonstrate more features later. For now, let me clear the console, make sure you have PM2 installed, stretch, take a moment's rest, and in the next video, we'll step beyond the basic functionality. We'll take a look at some of the really useful things that PM2 allows us to do when managing live clusters of node processes. I'll see you soon. Welcome back. When we're in development, we don't use PM2 so much beyond configuring it and testing it periodically to make sure that our cluster still works after any changes. But PM2 really shines when we're in production and we have a live cluster. We're going to take a look at some of those things that PM2 allows us to do that would be quite difficult to duplicate with the built-in node cluster functionality. Let's start with a fresh cluster. I can delete any of my running processes from the list of processes that PM2 tracks by running PM2 delete and our server is called server. There we go. We have no running cluster. Now I'll clear the terminal, and we can start our server using pm2 start server.js. That's the name of our main JavaScript file. And we can also use this -l flag to specify the name of a file to send our logs to. Let's say logs.txt. We can't forget, if we want to run our server in cluster mode, to pass in the amount of instances using the -i flag. So let's match the amount of instances to the amount of logical cores in our machine, which we can do with the max argument. Let's start our cluster. We have 8 instances, and we have some basic information about the overall status of each process. We could get more detailed information about each of these processes by running the pm2 show command and passing in one of their IDs. Say the first process with ID 0. And if I scroll up, we have these fancy code metrics showing the amount of memory that we're using, and even some information about the node event loop and how long each pass through the event loop is taking, what the latency or wait time is when running a command on the event loop. Scrolling up, we can do a lot more advanced things and get information about the process that's currently running. How long the process has been running. The path to the logs that we just specified, and the path of the script. Just like we can get information using the pm2 show command, we can also manage each of our processes from our pm2 list. So maybe we've detected a problem in the process with ID 4, and we want to temporarily bring it down to see what effect it has on the rest of the cluster. So we can do pm2 stop, passing in an individual process ID, like 4, and that individual process can be managed directly by pm2. When we're ready, we can start each process up individually as well. pm2 start 4. And all our processes are back online. Now we can check our project files and notice we have a logs.txt with all of our server logs, showing each of our processes and each time they were restarted. All right, to wrap up our overview of pm2, we can use this pm2 monit command, short for monitor, to get a fancy dashboard right in our terminal. It's not going to look so great in this small terminal over here, so I'll open it up in a separate terminal outside of VS Code. I'm in my performance example folder. I can do pm2 monit, and I get this live dashboard of the status of each of our server processes. As they accept incoming requests, we can see what effect that has on the memory being used by that process, or the CPU usage. We should see the CPU usage go way up when we make a request to our server, like the one with the timer endpoint, which uses the CPU to really quickly spin doing nothing. That's what our delay function in our server was doing. So let's make a request to our server and see how that affects the monitor dashboard. I'll refresh the timer endpoint on port 3000, and it's taking about 9 seconds. So we can see our first process was using 88% of the CPU. Now it's back down to 0, so in our server, we should see the request has completed. All right, in the next video, we're going to look at how to use PM2 to do something called zero downtime restart. It's going to be a really good one, so I'll see you there. Welcome back. Say we have our cluster running, just like we can see with our PM2 monet command that's on the screen right now. But we've been tasked to make a change in our server code. Maybe our timer now, rather than making a ding sound, needs to make a beep sound. Beep, beep, beep. Our server code has changed, and we now need to restart our server to apply our changes. But we have live users. There's people using our application, and we want to make sure that our application is still available to them while we make these changes. No one likes browsing to a page on the internet and seeing a notification about scheduled downtime, or worse off, unscheduled downtime. These situations can very often be avoided by doing zero downtime restarts, just like what we're going to do here. And maybe as part of our change, we want to decrease the delay to be only, say, 4 seconds. We'll save our server.js, but if we go to our browser and refresh our endpoint, well, it's still running the old version of the code. It's still going to take 9 seconds for this response to come back. Check that out. What we could do, in our terminal, we could restart our server using PM2. PM2 restart server. But there would be a point where our server is unavailable to all of our users because all of the processes are shut down, and then maybe they take a little while to restart. With zero downtime reload or restart, instead of terminating all the processes and restarting them all at once, we can use the PM2 reload command. Notice it's reload and not restart, to restart processes one by one, keeping at least one process running at all times. This is the best way to update servers that are already live and serving users, particularly with applications that are time sensitive. We want our users to be able to access our application 24/7, any day of the year. So let's see what happens if we run PM2 reload server. We'll see our updated code being applied and our processes restarted. And if we had this monitor dashboard open at the same time, we would see that each server is being brought offline one by one. We can now see that the uptime for each server is in the 30-second range. Now, when I make our timer request, 1, 2, 3, 4, there you go. We get our beep timer instead of our ding timer. Zero downtime reloads are all about making sure your applications are available to your users at all times, even when changes need to be made to your code. All right, that's all for now. I'll see you in the next one. Welcome back. Remember our final project? Based on what we've learned, we know we should use PM2 to take full advantage of all the CPUs in our server machine. How might we apply this to our NASA API? Our API doesn't have much long-running blocking code. We've been fairly smart about that. It can safely handle thousands of requests. However, at some point, the bottleneck will become the CPU and how many requests per second we can handle on the single-threaded event loop, right? Just like this IKEA bottle, the neck part determines the overall fastest rate at which water can flow out of it. The width or capacity of the rest of the bottle doesn't matter if the bottleneck is holding it back. So if the single CPU running our project API becomes the bottleneck, we need to try to set up a cluster with our NASA API running on each worker in that cluster. What we can do is go into our project's server folder. So we'll cd in our terminal to server and run npm install pm2 as a local project dependency and not as a development dependency. Now that pm2 is available in our server, let's update our package.json and add a cluster command that will run in production when we need the maximum performance from our server. So let's say that the cluster command will run pm2 starting our source/server.js, just like our other commands. And we'll start it in cluster mode using the -i flag with the maximum amount of workers to match the amount of CPUs that we have. pm2 is available in our package.json because it's been marked as a dependency when we installed it. So now in our package.json, in our project root, we can create a version of our deploy command here. Let's take that and copy it. And we'll say that deploy-cluster will do what the deploy command does with building the client and then starting the server here. But instead of npm start in the server project, we're going to run npm run cluster, which is the command that we just added. Let's see if our cluster works. I'll go back, and in the root of our project, we can now do npm run deploy-cluster. Node is building the client side, the front end. That's been completed, and we've started our backend cluster that's serving both our client and our API. So now in the browser, let's go to our project URL. Localhost on port 3000, or was it localhost on port 8000? That's the one. There's our beautiful dashboard. We can now create launches and send them to our server running on each of those worker processes. And if I go to my upcoming tab now, I should see all of my launches that I've created, right? We have one scheduled for December 27th and one on March 29th. Well, let's keep creating launches. I'll make one more for June. And submit that. And wait a second. What happened to the other launch that we just created? We're only getting the hard-coded launch that we had before, and the one that we just submitted that's scheduled for June 2023, but not the third one, which we expect to see. And it's definitely not in our history because we haven't aborted that launch. What's going on? Something about our cluster is making our dashboard seem like it's not saving the launches that we create. Let's get to the bottom of this mystery. Where are our launches being saved? That was happening in our source folder, the one in our server, /models and the launches model, where we keep this map of launches in memory while our process is running, in the memory of our node process. for the duration as long as that process is running. When we run our NASA project as a cluster, we now have multiple processes that are each storing a map of launches in their individual memory, and that memory isn't being shared. So if I send a request to save a launch to one process, and then I submit another request to get the launches, there's no guarantee that those two requests will talk to the same server, to the same process. For our clusters to work, and for any of our horizontal scaling approaches to work. Remember, when we add many servers together to each share the load for part of the requests that come in, we need to make sure that our server is what's called stateless. None of these servers can store state on them individually because there's no guarantee which server will handle a request coming in. The solution is to remove the state from our server's memory and persist it somewhere else. Somewhere like a database that lives independently outside of our node processes. So for our launches model, for example, we need to move this launch data, and rather than storing it in a map in memory, we need to store it in some database. A database that will have the added benefit of keeping our data around even if our server crashes or we have to restart it. We'll find out how to work with databases and persist our data very soon. I'll see you in the next video. Welcome back. Before we move on, there's an exciting feature in Node that I'd like to introduce you to. We're talking about worker threads. This is a built-in module that enables the use of threads to execute JavaScript in parallel. Worker threads are useful for performing CPU-intensive JavaScript operations. Those operations that would otherwise block our code. Whoa. I know what you're thinking. Doesn't our JavaScript code run on a single thread? Was everything that we learned earlier in the course wrong? Don't worry. Everything that we've learned so far very much applies. Worker threads don't change how Node works at the core. But they do add something new. Worker threads take Node just one step closer to making JavaScript a multi-threaded language. But not exactly. JavaScript, the language, doesn't have multi-threading features, and that won't change anytime soon. So what's the difference between traditional multi-threading and worker threads in Node? What exactly do worker threads do? To understand this, we need to look at the bigger picture. Worker threads in Node are based on the web workers that are available in your browser with the Web Worker API. Web workers let you run a piece of JavaScript code from your browser that's right, a worker thread. But in Node, they're a more recent feature. A feature that's still evolving as we speak. Worker threads were introduced thanks to a shiny new feature of the V8 engine called V8 isolates. V8 isolates are isolated instances of the V8 engine. You can think of them as these sandboxes that run JavaScript code independently of each other. Worker threads use these isolates to create new threads that can execute your JavaScript code side by side, with each V8 isolate handling the JavaScript code for one thread. What this means for us in practice is that worker threads, just like clusters, help us to take advantage of the multiple CPU processors in our machine. So worker threads are similar to the cluster module, but they do things very differently. The cluster module uses processes, while worker threads use this V8 isolate. Why does this matter? How does this difference affect us as developers? Let's explore these questions by comparing how the two work. To recap, our cluster module allows us to start a server which creates a master process that can then use the fork function to create child processes or worker processes, which can do things like respond to requests in your server. And you can call fork however many times you like to create new workers. We're very familiar with this flow. In comparison with worker threads, when we run our JavaScript file, we create what's called the main thread. This thread can use the worker constructor to create a new worker thread by calling new on the worker constructor. And just like with the fork function, we can create as many workers as we'd like. If this seems very similar to you, that's because it is. If we look at them side by side, the flow to create worker threads and processes follows the same structure. Basically, you can think of the cluster module as allowing us to run multiple instances of Node in separate processes, while the worker thread module allows us to run multiple instances of Node in the same process by taking advantage of that V8 isolate feature that we mentioned. We'll see this whole flow in action when we write some code to take advantage of worker threads. There's also some very important functional differences between worker threads and clusters. If you're paying really close attention, you might have noticed that with the worker thread example, I'm not calling my JavaScript file server.js, but instead index.js. This is to highlight the difference that each worker thread here is not designed to share requests coming into a server. The worker threads module doesn't include any built-in functionality to run a server on one port and distribute incoming requests between each thread. No, that's specific to the cluster module. So we could run a server using worker threads, but we'd have to implement that distribution of work ourselves. And here's the main difference. Unlike processes made with the cluster module, worker threads can share memory between each other. We'll see this in action in the next video. For now, what we need to know is that the worker thread approach isn't as rock solid as the cluster approach with multiple processes. This cluster approach, which has been used in Node since pretty much the day that it was created. In production, I highly recommend you stick with clustering for your servers. But that's what makes worker threads so exciting. There's still a lot of potential behind how they can be used, and it's definitely an area to watch out for. On that note, let's find out how to use worker threads in the next video. I'll see you soon. Welcome back. How do we use worker threads? Let's put this shiny Node feature to work. I've created a threads example folder, and I'm going to make a file that I'll call threads.js. To put our threads to use, we need to require the worker threads module. And I'll take a few different values from that module. The most important value will be this worker constructor that I'm going to destructure from the exports of our worker threads module. And similarly to what the cluster module allowed us to do, we can check if we're currently in the main thread or in a worker thread by using this isMainThread value that's also made available in our worker threads module. We can combine these two features to create new worker threads by calling new on our worker constructor. And the worker constructor takes a parameter, a string, that points to some file that contains JavaScript code to be executed in that worker. So what we can do is pass in the current file's path by using the __ file name value that's available in our Node modules. So __ file name will point to threads.js. And as it stands, this code would create workers over and over until our machine can no longer create workers, right? Because we would run our program, it would create workers that run our program again, which just create more workers forever. So what we want to do is only create new workers if we're in the main thread, when we run threads.js for the first time. So we can check is main thread and only then call new worker. Otherwise, what we'll do is we'll console.log that we're in a worker. To demonstrate how this might be used, let's create just two workers that both run the same code, the code in our current threads.js file. So if we run this, what do you expect to see? I can run node threads.js, and we have two worker threads that were executed, both with the ability to run our worker code in parallel. But let's demonstrate how worker threads are different from processes. Remember, worker threads are all part of the same process. Unlike clusters, we run Node multiple times in one process. So if we console.log using our template string that the worker's process ID is equal to this built-in process.pid value, and we can do the same thing for our main thread. We'll console.log right here at the top that the main thread has this process ID. We should expect to see, unlike our cluster module, 3 identical process IDs. Let's see. I'll clear the terminal and run node threads. Check it out. Our main thread shares the process ID with both of the workers. All right, so this is all fine in theory. But right now, our worker thread isn't doing anything useful. Let's give it some actual work to do in parallel with the other worker thread. What work can we give it? Say we have an array of numbers, something like 7, 6, 2, and 3. Remember that our built-in JavaScript sort operation that we can call on any array was blocking. Say we wanted to sort a few different arrays on separate threads to take advantage of the multiple CPU processors on my machine. We can send work from our main thread to our worker threads by using this second parameter to our worker constructor, which accepts an object with a worker data property. We can pass in the array we want to sort in each worker as the value of this property. So say 7, 6, 2, and 3. And for the second worker, we can send a different set of data. So worker data could be 1, 3, 4, and 3. This data will now be available in the worker thread inside of this worker data value that's part of our worker threads module. So what I'll do is I'll move our imports all onto a separate line. And right below is main thread. If we import worker data, this value will now be set inside of each of our worker threads. Say we wanted to log it, we could do console.log and then say that the worker data, which is coming through our import here, is equal to that value. And we could then do the hard work of sorting that array and saying that this worker data sorted is equal to worker data.sort. Now, while this sort operation will block each thread, because I have multiple processors on my machine, the 2 different arrays that I pass in can be sorted in parallel, side by side. Let's see what happens if I run our program here. I'll clear the terminal and say node threads, and you can see what happened is the main thread started, and then each of our 2 worker threads started, both doing our sort operation more or less side by side. Sorting is a fairly expensive operation when it comes to how much of your CPU it uses. By using worker threads, we can multiply the effectiveness of our CPU by taking advantage of its multiple processors. Processors which can run each thread in parallel. And because we're using the worker threads module, all of this happens inside one process in the most efficient way possible. Good stuff. I'll see you in the next video.